We're good.
Okay.
Okay.
It says recording in progress, and if for some reason the sound disappears during my talk, please try to warn me, because I'm always scared to death of something going wrong sometime in the middle of everything.
Okay, I think we'll hope for the best, and I'm going to go ahead and start the introduction. Hello, everyone. Welcome back to the Codex seminar. Today, our speaker is going to be Palle Jorgensen, who's going to be telling us about harmonic analysis and frames for fractal IFS L2 via infinite products on projections. Before we get started, a couple of standard announcements. If during the talk you would like to ask a question, please feel free to unmute yourself and ask the speaker. However, please do keep yourself muted at all other times if you are not asking a question. Additionally, this talk will be recorded, and so if you don't want your voice recorded and put onto our YouTube channel, you have two options. One is you can type your question into the chat, and one of the organizers will ask the question for you. The other option is you could wait until after the talk for the question and answer period, which will not be recorded. So with that all said, we're very excited to have you here today. Please take it away, Palle.
Thank you very much, and thank you everyone for coming. And I'm so happy to get to meet you again, even though it's just on the screen. Okay, so the thing that I always try to do first is give a rough idea what the words in the title are about. So the harmonic analysis will refer to a version of a Fourier expansion in some L2 space. So that's number one. The way we would build the Fourier expansion would rely on machinery for constructing frame. However, it would not be a frame expansion because the Fourier functions would not be frames. However, we would do what we call sometimes an auxiliary frame or dextrodual frame, and that the purpose of that will be to allow us to create Fourier coefficients so that our Fourier expansion will expand a general L2 function in as a limit of linear combinations of Fourier functions, and the Fourier coefficients would be in little L2 as it should be. And so that is that. And then the other one was the abbreviation IFS, that stands for iterated function systems. And so it's a general machinery for that's inspired by Cantor constructions. So take your favorite Cantor, like the middle third, then you want to live out the middle, so you translate the unit interval in the first third and the last third and a gap in the middle, and then you iterate that, and you then get a limit which is a set called the Cantor set, but you get another limit which is a measure which we call the Cantor measure. And so that was one more item. And then the machinery we use for that will be a system of operators that we cook up from projections. Of course, in the application to Fourier, the projections will be one-dimensional projections onto the Fourier functions. And we'll do Fourier in higher dimensions as well. So that means the Fourier functions would be e to the I x dot n, where x and n are vectors, but x is a vector in d real dimensions, and n is an integer vectors, again in d dimensions. And the way we would build our generalized Fourier expansion, it'll be enough to have a positive frequencies. So for example, if you are in 2 dimensions, then the Fourier frequencies would be the integers in the first quarter plane, because that's where both n1 and n2 are positive. So that is the introduction, and so I hope that helped a little. And so the other part of it is that there's an algorithm that we call the Kaczmarz algorithm, and it really comes from a linear algebra problem, but we extend the idea to infinite dimensions, and we extend it in the framework of Hilbert space. But what we really have in mind is where the Hilbert spaces are L2 mu, where the measures mu are these IFS measures. So think of them as generalized Cantor measures. So that's one thing. Maybe I should just give a little bit of history. More than 20 years ago, with a colleague, with a collaborator, and actually a former student from a very long time ago, and actually, I guess we're both Danish, but we invented, we played around with whether you can create a Fourier expansion on L2 or mu, where mu is a Cantor measure. And turned out that Bob Strichartz was interested in the same problem, and he kind of, I guess he had some earlier paper, and we guessed from his earlier paper that he was convinced you could not do Fourier expansions on these type of Cantor measures. And now we did it anyway, but we could only do it for a special class of Cantor measures. And then we build these orthonormal bases of Fourier functions, and the Fourier functions turn out to have lacunary Fourier expansions. So if you scale by 4, then you have lacunes that are separated by powers of 4. And so I guess lacunary comes with the waves you see in water that spread out with gaps. I should Google that, but okay. But one of the things that we had, and this is again the history here, you can do it for some, but not for all IFS measures. So if you go to the Cantor, you have a Cantor where you scale by 4, and then we've got an orthonormal basis. We have a Cantor where you scale by 3, and then you can't even get more than 2 orthogonal Fourier functions. And that's what we did. And but then you can go to higher dimension and you find lots of cute orthogonal Fourier expansions, but for some of them you can't. And so if you want Fourier expansion, you have to give up orthogonality. And so that was that part here. But then when Fuller saw our paper, actually he was a referee, he told us, then he was so excited and he congratulated and he invited me to conferences, and so many fond memories of working with Bob Strichartz. Sadly, he died a year ago. Okay, so that was another piece of introduction. So I think, and so here we'll invent a system of projections. So it's not Gram-Schmidt, but Gram-Schmidt gives you orthonormal, and I told you that you generally don't have orthonormal, so it's not Gram-Schmidt, but we can say that it's inspired by an algorithm that's a little bit in the spirit of Gram-Schmidt, named after Kaczmarz. Okay, and introduction, and here a few more punchlines that we would build up the machinery we need in the context of Hilbert space and projections. But what we really have in mind is a system of one-dimensional projections, where for each Fourier function, we take the one-dimensional projection onto it. But it's convenient to formulate in the language of Hilbert space. I don't know, I guess I learned Hilbert space in kindergarten, so I always think in the language of Hilbert space, but well, not quite kindergarten, but if you don't like to think in the language of Hilbert space, and think about it as L2 or mu, where mu is one of these measures. But the important thing is that we would like to extend some of the results that we had previously in 1D to higher D. So in other words, where the measures mu are these generalized fractal measures, also called IFS, but they're supported in higher dimensions. So that's one, but compact support, yeah. All IFS measures have compact support because the way they arise as limits. So if they arise as limits as scaling down, then of course you can imagine that they sit in a compact set. You can also think about them as chaos, so examples of chaos. So if you teach dynamics, which I do at the moment, then I like to think about these examples as examples of chaos. Chaos is used more or less if you have some kind of limit and you have no idea what it is, then you call it chaos. Okay, so here we go. In 1D, going back 200 years, we have Fourier expansions on periodic functions. So if we make them period 2 pi, then the Fourier functions are e to the INX. And we know all of that. And so to generate L2 of Lebesgue measure on the period interval, then you need all the integers, both positive and negative. So all the Fourier frequencies are needed if you want to do all two functions on the Lebesgue measure restricted to the period interval. But we're not interested in Lebesgue measure. And so it turns out that for fractal measures, you should not look for all the Fourier frequencies. You should only look for the positive frequencies. And the fact that the distinction between positive frequencies, or all of them, is closely tied to the nature of these fractals, or you can call them chaos attractors if you like that. Okay, so to get started, I'd like to remind you of a 1D fact from the Rudin analysis, and it's called F&M Rees. And normally you have that if the positive frequencies are dense, then the measure must be absolutely continuous and it's a Poisson transform, etc. But if you turn it around and you look at L2 or mu, and you want the Fourier functions for positive integers to be dense, then that happens precisely when the measure is singular. Why? Because if you have an f in L2 or mu that's orthogonal to the E lambdas, then f d mu must be absolute continuous. But if mu is singular, that forces f to be 0. So that means that you can rephrase F&M Rees as a statement about the L2, the Fourier functions being dense in L2 or mu. And so that happens precisely when mu is singular. So that's a lot of measures. So there are many measures that are singular that are not necessarily chaos measures or IFS measures, but we'll come back to that later. Then some of the work that I did, there's a bunch of co-authors. Some of the recent work is with the 3 co-authors, Chad Berner and John Herr and Eric Weber, both from all 3 from my neighbor university, except I guess some of them moved. So then the historic paper where we created orthogonal Fourier expansion for special countermeasures was Steen Pedersen, and then there were papers in between that and the ones where we use new machinery here, and the names that I like to mention there are Dorin Dutkay, James Chiang, and Min-Sin Sung. And then we're also inspired by frame results of our good friend Pete Kaczmarz. So that I just want to make sure that I don't forget the important names here. And so you can guess in the last line where the H and the J and the W, H is Herr and W is Weber, and so on and so forth. Okay, and I'll show you a very small sample of references at the end, but the papers contain a full list of references, so we'll get to that shortly. Okay, so here we go. The new direction here dates just a few years with my friends and co-authors from my neighbor university, and it goes like this. So we were talking, and the subject was how do you do you cannot do F&M Rees in higher dimensions. So how do you get around that difficulty? Well, if you want to do analysis for measures in higher dimension, then you would have to somehow split them up in slices, and this is something I've done all my life for different problems, but creating direct integral Hilbert spaces. But take the simplest slice situation here, which is a 2-dimensional measure. And as I say, I'll just assume that it's supported in the square, because the examples will look, and that'll be good enough. And how do we create slices from it? Well, we can take the first coordinate and we can take the distribution of the first coordinate pi1 relative to the measure in 2D. Well, that's just the pullback by the coordinate projection, and so that gets you from a 2D measure to a 1D measure. You can do that in any probability space. If you have a random variable, then the random variable is a measurement on the real line, and it has a distribution, and the distribution is the pullback of the random variable. In this case here, the random variable is just the first coordinate projection, but it still has a projection. It still has a distribution and so on, and so then you get a 1D measure, but that 1D measure is marginal, so it doesn't tell you about what goes on inside. However, there's a beautiful theorem that I usually call the Rocklin theorem, but people in statistics call it the theorem about conditional measures. So what is a conditional measure? The conditional measure is a measure that's conditioned on the function we want to study being equal to x. So if the function is the first coordinate function, then pi1 is equal to x, is conditioning the measure upstairs by a fixed x value. And so if you're in the square like this, you can just think about it as a vertical line in the y coordinate that crosses through x. And so there's much more general formulation of slices, but this one here is a way to write a measure in higher dimensions as a direct integral of conditional measures, and so we'll have that. In probability theory and statistics, they call it the Bayes rules. The Bayes rules is how to build measures from conditional measurements. Okay, so there's that. And so let's stay with 2D just a little longer. And so here I wrote down the Fourier functions, and so that would be n dot x, and both n and x are two-dimensional vectors, but the Fourier frequencies is the one with the integers. And so for these particular chaos measures, it turns out that you should look for the Fourier functions to be supported only in the positive Fourier direction. So if you're in 2D, that would be the first quarter plane, or the integer points in the first quarter plane. So that was one thing. The other good thing about this is that then you have at your disposal Hardy spaces, and so there's a beautiful theory of Hardy spaces, both in 1D and in higher D, and we'll get to that later. All right, so that was the ingredients in this theorem. But here's what the theorem says. The theorem says that if you want these special Fourier frequencies to be dense in L2 or mu, then being slice singular is enough. And so that's only one implication. Slice singular implies dense. With sometimes this density property, we call it effective. I truly believe that there's a converse, that if you have the Fourier functions having dense span, then I think there's a theorem that says that then you can create a slicing for L2 or mu that where each slice is singular, but that's a conjecture and it's not a theorem. But this one here is a theorem that slice singular implies that the Fourier frequencies have dense span in L2 mu. So that's kind of like the beginning of Fourier expansion, but it's only the beginning because it just says that the Fourier functions are dense. It doesn't tell you how to calculate Fourier coefficients and write every f as a Fourier expansion in terms of Fourier coefficients. So the main purpose of the talk is to build Fourier frequencies. So we'll get to that in a moment. And here are my two favorite examples of slice singular measures. And I'll get back to the nitty-gritty of them. But you can see that the slices intersect These two are my favorite fractals, the Pinsky-Gaskin and Pinsky-Corbett. You can see that the slices in the vertical direction intersect them in gaps, and it's easy to see that the one-dimensional slice measures for almost all x will be singular. So that's one part of what's required. But what about the marginal measures? If you look at that the x-coordinate and the y-coordinate, you see that the x-coordinate doesn't have any gap. So what is he talking about? He's telling us that the marginal measure is singular. How can it be singular if it doesn't have any gaps? The reason is that that two ways to create chaos, and one is to have the two half intervals without gaps having assigned equal weights, so a fair coin, or unequal weights. But you can see that the first half of the unit interval in the x-coordinate has weight 2, and the other has weight 1. So you have an IFS measure that's built up by these scaled down measures here, but with different weights. And I don't know if I managed to get to the nitty-gritty of the important role played by the weights of the components in an IFS construction, but it turns out that for every system of weights in such an IFS construction, you get a measure, an IFS limit measure, and for any distinct weights, these measures would be mutually singular. So if I do the fair coin weights half-half on the x line downstairs, then obviously I get the big measure, but I don't have 2/3 and a third, and that's different from a half-half. And so the theorem of Kaczmarz about infinite product measures tell us that the marginal measure on the x-coordinate is a singular measure. And so that relies on a cute little application of a fantastic theorem, one of my favorite theorems of Kaczmarz. Okay. So then the other one, the same story here. You can see in the vertical direction, they clearly have gaps and they're singular. What about the x-coordinate? Well, it's weighted differently. So the first and the last of the three parts of the partition of the unit interval in the x-coordinate have weights 3/8, and the middle one has weights 1/4. And so you have unequal weights. And so the marginal measure, even though it looks like it doesn't look singular, but because of the weights being not uniform, they're not a third, then because they're 3/8 and a 1/4 and 3/8, then by Kaczmarz, the marginal measure is also singular. So here you have two nice examples of slice singular measures. So that means that the corresponding Fourier frequency functions we talked about in the previous slide, they are total, or rather they have a dense span in L2 of these fractal measures here, IFS measures. So there's a Sierpinski-Gaskin with a canonical measure that has its support equal to that, and there's a Pinsky-Corbett that has blah blah, and so that's what I mean by IFS measures, singular measures. And so not only are the IFS measures singular, but they're also slice singular. Most IFS measures in high dimension turn out to be slice singular. You'd have to really twist your mind to get one that's not slice singular. Okay, and so this one here is just the general framework of IFS measures in high dimension. In high dimension you have a finite system of maps in RD that are contractive, and then as you go through the sequence of rescaling, then in the limit you get an IFS measure, and they're generalized Cantor constructions, if you like, or chaos constructions. I think that's enough for that one here. And this one here mentions the items that I mentioned in the introduction here: frames, projections, and Kaczmarz. And I'll get to what they mean. Okay, so Kaczmarz is actually, if you think about Kaczmarz, then it's easier than Gram-Schmidt. It's just that you have a sequence of spaces, and then you project from one to the next, to the next, to the next. But you don't take products of projections, you take products of the complements of the projections. But this one here is the one that Kaczmarz invented for solving the matrix equation AX equal B. Then he takes projections onto the hyperplane. And the third bullet point is the one where you just take an arbitrary sequence of vectors in your favored Hilbert space, and then you iterate the projections onto the individual vectors. And but here's my picture of it. If you have a matrix equation on the left side, then it's AX equal to B in 2 dimensions, and so you have 2 hyperplanes, and then you start with any point in 2 dimensions, you project onto the first hyperplane, then you project down to the second hyperplane, back to the first, back to the second, but at each step you use the orthogonal complements of those. And if you give me any sequence of vectors in a Hilbert space, then you project the first onto the second, and the second onto the third, and so on. But it's not the projections you want, it's the orthogonal complements of the projections. And so we'll get to that in the next slide here. There they are. So you give me any old, your favorite sequence of projections in the application that I have in mind here. There'll be 1-dimensional projections. So each of the projections Pn would be the projection onto a Fourier function En. But the way I'm going to formulate it here, it applies more generally. So this is a statement about any old countable system of projections in a Hilbert space. And so we want to do an analog of frames. And so we take the product of these complementary projections. So if you have projection onto a subspace, then projection onto the orthogonal complement is 1 minus P. And then you iterate them, and then you get a sequence Tn. And then you want to construct another sequence for building frames of a generalized kind here. And the other sequence is called Qn, and it's the same as before, except that when you go through them, the complement of number 0, the complement of number 1, etc., then you give it a kick in the tail, and you put in Pn instead of the orthogonal complement of Pn. So then you get another sequence Qn, and that's probably this kick in the tail is probably the part of this construction here that's maybe a little bit analogous to Gram-Schmidt. In many ways, this is easier than Gram-Schmidt because you only do one step at a time. Okay, so then you have these 2 sequences of projections, and you want to play around with them to get something that looks like it might be a frame. So you took Q star Q, and you add them up to N, and then that would be a positive operator, which you write as 1 minus T star T indexed by N. And you add up the Q's from 0 to N, and you write that as 1 minus Tn. And so the theorem says that one is convergent if and only if the other is convergent. And so we're interested in the case where the Tn's go to 0, because if the Tn's go to 0, then you get an operator formulation of a frame. Okay, so is that what I wanted? Yeah, I think so. Okay, so the corollary here in this construction is a corollary of the formula that we had for the Tn's and the Qn's. Remember that both the Tn's and the Qn's were constructed from an initial sequence Pn. And so condition number 1 is the condition that you would guess should be the condition of a projection frame. And condition number 2, it turns out to be equivalent to that. And that's equivalent to number 3. So the Tn's are kind of the error terms in frame expansions here. And so the the corollary here is I just mentioned one paper where we flesh that out, but and S is Sung and T is Jiang. Okay, so that was operator frames, and here I just told you what my definition is going to be, but here it's made a little more precise. The sequence Pj here has the properties we're talking about, and it's called effective. Now, if the the Pj's are projections onto one-dimensional spaces here, then you have a sequence of vectors, and so the Pn's having this property here is equivalent to that sequence of vectors being effective, which we define to having a dense span. And so that's what we're aiming for if we want to build Fourier expansions. And so I just rewrote the definition of what we would mean by frame. And so you can see that 8 and 9, if you specialize to one-dimensional situations, 8 and 9 would then be the familiar definitions of your favorite frames. Okay, but now I want to call attention that our aim is not to build some crazy operator systems for no purpose. Our aim is to create Fourier expansions on these general L2 mu spaces. So, and our aim is to start with the Fourier functions En or Ej. I run out of discrete indices, so I call them Ej. and then we have the corresponding one-dimensional system of projections. But now I want to say another thing, and that is that this is a place where Dirac's bra ket and ket bra terminology is great. I actually learned Hilbert space in a quantum course, and so my first exposure to Hilbert space was the Dirac terminology of bra ket and ket bra. So you all know that a bra ket is an inner product, and a ket bra is a rank 1 operator. Take equation 10. That's the rank operator, and if you hit a vector x with it, then it'll be the bra ket with gj and x, and that would be a scalar times the vector ej. And remember, the vectors are kets. And so this one here is just sending an arbitrary vector in the Hilbert space into a scalar times Ej. So that's what we're aiming for if we want to build Fourier expansion, if we want to take the Ej's as being the Fourier functions here. But the thing that's especially exciting is that if you use the projection language here, and if you go from the sequence Pj to the sequence Qj, then Qj would be a rank 1 operator, and one of the vectors in that rank 1 operator, and the ket bra operator, is the one you started with, so that's nothing new. But the other one will be an honest possible frame system. And so this one here is a reformulation of our theorem about possible frames, that the G part of the Q system will be an honest possible frame if and only if we have this dense span property for the Fourier functions. And so, of course, we want to get the dense span property for the Fourier functions by doing the slice measures. So for the slice measures, we show that the span of the Fourier functions will be dense. But why do we want that? Because then we can build Fourier expansions. How do we do that? We have to get our hands on a partial frame so that we can define the Fourier coefficients using that partial frame. And that's the G system. Okay, so far so good. Here I rewrite the P's and the Q's the same as we have it before. And then I specialize to the Fourier, but I just look at a general system, E0, E1, and so on and so forth. And then equation number 14 shows you that if I rewrite the algorithm in this language number 4 here, then I get a an explicit recursive formula for the G functions, and the G functions are the possible thing that I want. But I can do better, and I'll mention that briefly here, and I'll get back to it later. If you move the sum term on the right in 14 to the left, then you get an infinite lower triangular matrix with the E functions. So that I call that a Gram matrix. So you have two systems of columns, the G system and the E system. So it says that the infinite Gram matrix on the G system would give you the E system. Infinite Gram matrices are easy to invert. So that means that you get an explicit formula for the an explicit formula for the G system expressed as an inverse Gram matrix applied to the E system. So because as you look at number 14, it's really just a recursive relation, but this alternative formulation of 14 will be important when I get to the use of Hardy spaces on the disk, on the Palle disk. Yeah. Okay. So I'll move on here. This is just writing out what I said about creating a new sequence, G sequence from an E sequence here, and getting an honest possible frame made up of the G system. And at the bottom here, you have the usual definition of your possible frame that you've probably seen a million times. Okay. And so here I just remind you of the definition of effective. That means dense span, and so the corollary of what we did in the previous slide is that the G system constructed this way here will be an honest possible frame if and only if the E system, in other words, the Fourier functions, are effective. So that means you get a generalized Fourier expansion when these conditions are satisfied here. Okay, here's it turns out that that sometimes it's important to have a probabilistic approach. I was inspired by Pete Kaczmarz, and Pete Kaczmarz called them I guess he calls them fusion frames, and so if fusion is fusing them together, and so to get a formulation that builds on Pete Kaczmarz, it's convenient to look at random variables mapping into projections, and Hilbert's, assuming you apply the projections to vectors, so you get operator valued random variables realized in a probability space, and so we will then be able to translate our theorems about possible frames and generalized Fourier expansion into this probability framework here, and that turns out to be important for the way we realize these chaos measures here as limits, and that it's important to be able to if you are interested in a difficult question and you don't know if it's true for all parameters, then you want to show that it's true for almost all parameters, and for that you have to cook up a probability space that allows you to get conclusions for almost all. And an example of that is fusion frames as they're built by Pete Kaczmarz and his collaborators. So that'd be that. And then again, we then have a probability space. And so if you start with a system of projections, then we would have a random variable, and it will have a distribution, and that would be the probability of the random variable is equal to Pj. And that would be a system of probability weights. And the theorem that we're going to use to prove here requires that the Pj system satisfies a lower bound, which is that the expectation of the random variable squared on vectors x has a lower bound, which is a constant times the norm x squared. So that fits into a lower frame bound, if you like. And with all of that, we can then repeat what I did before, but this time here I have a sequence of random variables, and but they take values in projections. So the complementary projection is 1 minus that, and we do the product from 0 up to n. And for the Q1, we kick in the nth term instead of 1 minus the nth term. And so we get a Tn system and a Qn system the way we had it before. And the theorem is that with the previous assumption, then we have that this limit here built up from the Tn sequence here is equal to 0. And that means that the Tn system will be, it's a random system, but it'll be a Parseval system for almost all measurements in that probability space. So that's what the conclusion in theorem 15 is telling us. Okay, so let me just make sure I'm okay. I'm kind of running a little short. Here's a slight reformulation of that frame condition and the fusion frame and the probabilistic language here, and an extension to the case where the P operators might just be positive contraction operators instead of projections, and the theorem would still hold. And then I get to the isometries. That's where I bring in the Hardy space for the Palle disk here. And the first theorem on that is that there's a bijective correspondence between two things. One is isometries from L2 or mu into the Hardy space, and the other is Parseval frames, the GN frames that we talked about in the first half of the talk. And if you give me an isometry, then I have the canonical system in the Hardy space and the Palle disk, the multivariable z to the n. And then I hit that with the adjoint to the isometry, and I get a system of vectors in L2 or mu, and that would be a Parseval frame. And conversely, anytime you give me a Parseval frame, then I can construct an isometry that has these properties here. So that's how you extend some of the classical theory of the use of Hardy spaces for Fourier expansions to this framework here. But the main thing I want to stress is that the variety of all choices of these Parseval frame vectors Gn is in bijective correspondence with isometries from L2 mu into the Hardy space on the D disk. So far, so good. But you also know that there's a D-dimensional version of the Sega kernel and it's number 26 here. And if we want a map that goes from L2 or mu into the Hardy space, then you can construct it like in equation 27. You take an f in L2 mu, and you take fd mu, and you take the Fourier coefficients of that indexed by n in the multivariable case, and that's a number, and that you multiply that by the canonical z to the n function in the Hardy space, and turns out that that is the first step in building an isometry. The second step in building an isometry is to normalize it. So you just do it on the constant function 1, and then you divide, and you get the normalized Sega transform, and that'll be the isometry you're looking for. And then I go to the slices, and I'll show you that. Here's the isometry. So if you take these measures in L2, then you take the marginal measure and the slice measures, and then you construct isometries for each one of them. So that's how you draw inference from 1D theorems to 2D theorems, and then by induction to higher D theorems. So here's the theorem about the 2D version of these isometries. So each of the measure mu is slice singular. So that means that you you have an isometry for the marginal and for the slices. And so you apply the isometry for the slices to the second variable, and then you get a function in the x variable, and you apply the other one to that. And from the property of the direct integral decomposition coming from a slice, we see that the operator you construct by doing it this way here will be isometric and vice versa. So that means that from the slice decomposition property, you automatically get an isometry, and therefore you get a GN system of Parseval vectors. So that's that. And here's what it looks like. Right. And so in the remaining few minutes here, I want to show you a few examples of IFS constructions. They come from a system of contractive maps, tau B, indexed by a finite alphabet. And so we create a product measure by putting in weights on the finite alphabet, and the product measure is a Kaczmarz property measure. And then we take limits of these IFS construction, and the solutions to equation 34 is the IFS measure indexed by a choice of weights on the finite alphabet. And so the Kaczmarz theorem is that if you take distinct choices of weights here, then you get mutually singular measures like this. And here's how to build the link between infinite product measures on one hand, because if you have contractive maps here, then the intersection of a long word truncated applied to the space here would be a singleton. So that would give you a map from L2 of the infinite product space to be L2 of mu. And there it is. And so for every choice of weights on the finite alphabet, you get an IFS measure, and it satisfies the familiar properties here. But the only thing I want to emphasize is that that all these IFS measures are really distributions of the geometry coming from iterating an infinite system of contractions like this. And so this one here is a property that should be familiar if you think about Cantor sets, that Cantor sets are the union of the scaled down versions, possibly with gaps between them. And this one here is some non-overlap. So some of the conclusions are a little more complicated if the IFS has overlap. So for this one here, I assume non-overlap. And then the theorem is that that the corresponding IFS measure mutually singular for distinct weights, and that's the application of Kaczmarz. And then a few examples with the Sierpinski here. There's the Sierpinski coming from the Sierpinski triangle. So there we have three pieces of the triangle, and we scale by 2, and so that's the picture of the Sierpinski triangle. And so everything we talked about would apply to L2 of mu, where mu is the IFS from the iteration of the triangle here. And here's what the infinite alphabet iterations look like with weights like this. And this is a Markov chain. So the mu here could also be thought of as a Markov measure like this. And then we do then we use the definition of the Sierpinski triangle, and we take the Fourier transform, and we discover that the Fourier transform of the Sierpinski measure here satisfies a multiplicative rule here, because the original definition of mu was a sum rule, but when you Fourier transform, you get a multiplicative rule, and then you iterate that, and you get an infinite product. And so you see that all of these IFS measures have a Fourier transform that arises as an infinite product. And so that's and so that if it's an infinite product, yes, then each of the two components have a binary expansion with coefficient 0, 1. And so what we talked about here with the different weights is that if you do the the binary expansion for the two components here, then the weight for 0 is 2/3, and the weight for the other bit is 1/3. So a bit expansion with weights 2/3 and 1/3. And so that's how we get these the conclusions about the slice singular measure here. And there's a picture of it. And again, because the weights are 2/3 and 1/3, the marginal measure looks like this, and the other measures look like that. And so there's a Markov tree where, again, the weights are indicated like this. And anytime you have a Markov matrix, you also have a Perron-Frobenius vector. And so the Perron-Frobenius vector in this case here is 2/3 and 1/3. And if you do the Eiffel Tower construction here, then you get weights 3/4 and 1/4 for the partition in the two pieces here. And you get the value of the bits here are 3/4 and 1/4. And so it's singular. And if you do the Markov tree, it looks like this. And then the Perron-Frobenius vector is 3/4 and 1/4. And then we are ready to do a theorem here. And a conjecture. And so the conjecture is that we get the slice singular property and the Fourier property if and only if the Perron-Frobenius vector is equally distributed, so proportional to the vector that has 1 in each component. But that's only a conjecture. But the previous example should give some plausibility to that conjecture. But I have a feeling that I ran out of time. So am I out of time?
You could go. We started a little bit late, so if you have like 2 more minutes, we'll be fine.
Okay. In that case, maybe I'll go back to this example here. What it is, it's that we build since it sits in 3D, then we do a slicing starting with a marginal measure. And so the marginal measure is called C. And then the weights for the marginal measure depends on the rest of the fractal here. And they turn out to be 3/4 and 1/4. And this one here is, since we are building the IFS by iterating steps through a finite alphabet, then we can think of it as a transition matrix, which is a matrix that has some 1 on the row components add up to 1, so that it's a transition matrix corresponding to transition probabilities, and it's the entries are non-negative, and so it's an example of a Perron-Frobenius matrix. And for the stuff that we do here, we're interested in these weights. So the left Perron-Frobenius eigenvector is the one that gives us the weights that we're looking for. And so for this baby example here, the weights were 2/3 and 1/3. And so that's an example where we know that it's singular and has a Parseval frame Gn here. And so that's consistent with the conjecture here. And so the conjecture is that the main theorem that I mentioned in the beginning of the talk here, the main conclusion in the main theorem I mentioned in the beginning of the talk is valid if and only if the left Perron-Frobenius vector of the corresponding Markov chain is non-uniform. So you see this is non-uniform here, and this is the Markov chain. As you move forward in each step in the Markov chain, so it's stationary. It's the same transition at each step here, and there's the other one where you have bits but different distributions, and so like that, and if you create a binary system, and if you're in 2D, then you construct the binary expansion for both the x coordinate and y coordinate, And so the singular property is that the distribution of the bits should not be the uniform distribution, which we see here, that it's 2/3 and 1/3. That's a thing I mentioned in the beginning. And this one here is again a beautiful property of these Fourier transforms, that they have an infinite product. So normally you express an IFS construction for a measure like in 46, but we all know that measures are determined by the Fourier transform. And so in some sense, the infinite product formula is easier. Infinite product constructions for Fourier transforms are usually named after Bernoulli. So some of these special examples are often called Bernoulli infinite product examples. And so this is an example here. And I mentioned in the beginning that our theorem started with the simplest of all your IFS constructions, which are the Cantor constructions, scaling by 4 and scaling by 3, and then you get infinite product expansions. The properties of infinite product analysis here turns out to be very helpful in deciding when you have an orthonormal basis or not. Now, if you have an orthonormal basis, then your Fourier expansion is just the obvious one. But the purpose of the theorem in the beginning here was to construct some GN functions so that you can use the GN functions, the Parseval frame functions, to build your Fourier expansions. You start with the Fourier functions En, and then you look for the Fourier coefficients. And so the Fourier coefficients would be Gn, a bracket with En. And so if the GN system is Parseval, then that would be a Fourier expansion. It will not be orthogonal because the En functions are not orthogonal. However, it would be have the fantastic property that you always want a Fourier expansion to have, is that the L2 mu norm of the function should be the little L2 norm of the generalized Fourier expansions. And so the fact that this is true, it relies on the Parseval property that we create when we created the GN system using this projection machinery here. We created the GN system so that it'll be a dextrodual to the EN system. So the EN system can be checked not to be a frame. So the subject actually started out with the theorems that I mentioned about my work with Pedersen, where we got orthogonal expansions. So many people thought, well, if they're not orthogonal, maybe they're frames. It turned out that either we could prove that the EN system were not frames, or we'd get into a situation where it was impossible to decide if the EN system were framed. But if they were frames, they're certainly not Parseval frames. But so what this PN, the projection machinery, is doing is that starting with the property for the EN system and the slice singular property here, we build the GN system, and the GN system would be an honest Parseval, and the GN system would be the key, the natural thing that goes into construction of the little L2 Fourier coefficients in the Fourier expansion, where we expand a general L2 function as in terms of the non-orthogonal Fourier frequencies. So that I guess maybe I better stop here. So okay, thank you very much. Thank you very much.
I'm going to thank Palle by hitting this react button. I encourage you to as well. That's how we do this thing online. Now I'm going to stop the recording.